Okay, so welcome everybody to the first research session of LOPSTR this year. So welcome to the first research session of LOPSTR. So after the nice invited talk this morning, and we start with a paper on reusable machine calculus for automatic resource analysis, and Hector will present it. So please go.
Thank you very much, and thank you for having me. So, hi, my name is Hector, and I'm going to present the work I did to create a reusable calculus based on the stack machine for automated resource analysis. This is work I did with my PhD advisor, Emmanuel Chailloux, at the LOPSTR23, the computer science lab at Sorbonne University. So, what are we talking about here? So resource analysis, as far as we're interested in it, we want to figure out how much material resources, so time, memory, or energy, is used by a program written in a high-level programming language like ML or Haskell. So the problem is to recover operational behavior from those from the source code of those programs, while those languages really try to hide that from you. The approach we've taken is to use an abstract machine, which we hope is a good first bound between software and hardware, but also is sufficiently neutral to allow for portable analysis. And as we'll see, the main feature we're using is first-class evaluation contexts, and I'm going to talk more about that. At the end of the day, what we achieve right now is some functional imperative programs with explicit allocation and freeing of cost, and our analysis is implemented as an effect system for those programming languages. So what we're going to talk about is first what are the main techniques for resource analysis that we're going to use, and we're going to present our tool in a general sense. Then we're going to talk about the abstract machine ILL as is, then how to encode more traditional programming languages in the machine, and then give an overview of what everything looks like at the end. So, automating amortized analysis. So what are we talking about when we say amortized analysis? So if we consider this code that implements a functional queue, hang on, I'm going to put a pointer here. Yes, okay. So we implement a queue with a pair of lists. So we have a front list that represents the back of the stack. Well, we have a back list to represent the back of the stack, and a front list to represent the elements that are on the front of the queue. So when enqueuing an element, we just push it to the back of the queue. But when dequeuing, if we have someone at the front of the queue, we just pop that off. But if we do not, first we reverse the back of the queue to the front, and then we dequeue this. So if we're interested, for example, here in the amount of time we call the constructor for lists, what we see is that dequeue makes a call to reverse. That call to reverse makes n calls to cons, where n is the size of the list being reversed. So if you process n elements through the queue, we should get some quadratic complexity. But if we look at it in a finer way, we find out that every element is only flipped once, is only passed through reverse once. So in actuality, this code has linear complexity, and it's quite important in that case. And what we'd like to do is how to undertake those reasonings automatically. Here, what we're going to do is say that if we pay the cost of 2 every time we enqueue an element, we can pay one cost for the reverse and another one for the cons right here in the enqueue, which will be enough to get the result we want about linearity. So how do we formalize that? We formalize it by saying that programs are command C, which reduce their small step semantics. At each step, we accumulate a cost, which can be positive if the cost is paid, or negative if some resource is reclaimed. At the end of the day, what we get is the cost of the program is the maximal is a maximum partial sum over this entire execution, which represents the instant at which most resources are allocated at the same time. So to get a bound on this reduction, what we do is we fix a potential function on commands, which can cover every single cost, and then the initial potential is a compiled time bound on the cost of the overall program. The problem is, in order for this to work, we need our commands to be built out of value, which is a program we are computing, so a function basically, and it interacts with an evaluation context called a stack, which contains arguments for the function. And we know V, that's a program whose source code we have, but we don't know S. What we're going to do is we approximate this unknown parameter stack with some variables representing size and length of arguments, and at the end we want to instantiate some function p of n as our potential. So the way we do that, this can be done automatically using a technique called automated amortized resource analysis. The idea is to enrich the typing disciplines on functional languages with parameters at type level to represent length and size. Here, this list of 3 integers has length 3, and that's indicated in the types. So preserving the amount of resources allocated in 3 in the program gives you a constraint on those type level parameters at each point in the program. And you can accumulate those and eventually get a program-wide constraint on parameters. What you do is you try to solve this constraint in some consistent but not complete way to get some system of equations that you can eventually optimize to get a bound. For example, using standard HARA techniques, we can figure out that if n elements are processed, we do get a linear time for the functional queue we saw earlier. A recent formalization of HARA that we think is extremely important is given by lambda amor, which was presented a couple of years ago. And this is a lambda calculus with an affine type system. So you can take into account resource flow in the program. And it has a more mainstream type system than previous implementation, in that we have normal types and parameters, let's say integers, and we have dependencies of type on parameters. And in lambda amors, this potential function that we want to build is split over all potential values currently in the scope, and so each value holds its own potential. The way we encode this potential is using the type bracket p of t, which is some value with potential p. We have the type m p of t, which are computations that will incur a cost p, and then we have quantifications over parameters and manipulation of parameter constraints. Here this is implication and witnessing that some constraints hold. So the functional queues that we saw before can be expressed here by saying that a queue is data structures with 2 parameters p and q, whose sum is the full size of the queue. And the queue is a pair of lists, one of size p, one of size q, and it must hold 2p plus q potential to cover for its processing. So you can see here that the 2 lists have heterogeneous potential. And the type system of lambda amor lets us encode that at type level. So how are we trying to, so what are we doing how do we implement this in our system? So, so the main problem that lambda amor has that we're trying to solve is that there are no universal small step semantics for lambda calculus-based languages. So if I just look at function application, if I reduce it in call by name semantics, I just substitute the body of the argument. I just substitute the argument in the body of the function. But if I want evaluation in call by value semantics, I have to first evaluate the argument with continuation the body of the function. And if we pick one of those systematically, we can get eager versus lazy evaluations, but we'd like to be able to mix and match those evaluations to get some lazy monadic computations, to work with some iterators, and to work with some iterators to cover a larger body of functional algorithms in our programs. The reason this is complicated in current resource analysis system is because we can understand potential and resources using parameters that are put on types, which recover some structure in the data manipulated by the program. So a list has length, a tree can have depth and width, but in lambda calculus, computational contexts are not data. So we cannot use the same system to say this iterator will be called in that way, or this monadic action will be used in that way. And that's a problem. So what we do to resolve that issue is to use a defunctionalized continuation passing machine, meaning that the stacks that we talked about become just more data structures, and they can now be analyzed with the same techniques that Hara has developed to infer parameters on data structures. So Autobill is the project we implemented. It's a modular framework for automated resource analysis, and it supports main input languages. So a OCaml-like programming language with call by value semantics, but also a call by push value lambda calculus, and directly the machine with explicit parameter types. And as opposed to previous implementations of Hara techniques, we support arbitrary first-order parameters, meaning that you can define your own sorts and operations on type-level parameters and get a first-order constraint out of those. And it is available, it is open-source software. When we try to imitate previous Hara work, what we get is parameters are integers and functions on integers that are modeled by multivariate polynomials with integer coefficients. And in that setting, we can reduce the constraints to some algebraic problem that we can solve using the Minizinc solver suits, which give a pretty user-friendly interface to solvers and optimizers. And so we can recover the simple results we have for the functional queue. So how does this work? First, we have our input language, which is some kind of a functional statically typed lambda calculus. And the first thing we do is we translate it to call by push value evaluation, which gives us an explicit notion of control flow for the program. So the call by push value program will somehow embed its own operational semantics. Then we run a CPS transformation, which gives us our abstract machine notation. On this abstract machine notation, we can run a linear type inference algorithm, which can explicit data flow. So when is data shared? When is it just forgotten about? And finally, we can run our effect system, which turns a cost primitive into resource manipulations. So resources are being threaded into the entire machine at each step. And then we just run parameter inference to get a constraint and resolve the constraint using some solver if some solver is available for the theory that is used for the analysis in question. So what is this abstract machine, and how do we capture computational contexts? So the machine is based on a work by Curien and Al. So to study the computational interpretation of intuitionistic linear logic, and it's a machine with call-by-push value semantics, which means it has a thing called polarized evaluation. So what that means is there are two sorts of base types. There are data types, like data structures, which are evaluated eagerly, And there are computations like functions and funcs which are evaluated lazily. So we extend this machine with parameter polymorphism, with explicit sharing for tracking data flow, and some fixed points to represent loops and iteration. So the machine is either some data being processed by a stack or some computation consuming some evaluation context. And the values so far can be variable and binders. On each side, X are value variables and alphas are here are stack variables. And you have the obvious reduction in which when you bind something with a name, you just substitute the name. The polarized thing comes into play when we try to evaluate some ambiguous command here. So which of the binder wins? Well, if A and X have positive polarity, what happens is the data side wins, which lets you evaluate expressions that consume their computation context and produce some data. And if the polarity is negative, the computational context win and can process a computation before the computation is run. And this disambiguation is the key that lets us manipulate evaluation context and get unambiguous operational semantics on the machine. So what data structures look like is this. So we have here a data type definition for linked list. So it's a list of size n with element type A, and A can depend on its position on the list. So it's of sort natural number 2 pos, which is the sort of data. And the list is either a nil constructor, which holds no element and has size 0, or it is a node in the list, which has an element of type an, and a tail of the list, whereas a tail has size m, and we have a constraint that m plus 1 equals n. And we write it this way instead of n minus 1 to avoid the problems of subtraction not being quite a total function on natural integers. So in type definitions, we can introduce new parameters here with a where clause and introduce constraints on parameters which must be witnessed when some constructor is used. So we had to values this constructor with arguments, which witnesses that parameters exist and constraints are satisfied. We have pattern matching, which is classical pattern matching, but it will introduce universally quantified parameters. Universally quantified parameters on which the constraint is assumed to hold, and during reduction, whichever parameters were typed here are used to instantiate the universally quantified parameters there. And using those data type definition, we can recover many types from lambda armor, including linear data structures, quantification, the existential quantification over parameters, and witnessing some constraints. On the other side, we finally have our explicit computational context. So the idea is that our stack, which is data representing the context, is just a list of stack frames, so a kind of data structures. And a computation is just a thing that captures and matches on that data structure. And that gives us functions, lazy pairs with projections, as well as universal quantification. So here, for example, I have a stream data type, which will produce values over and over, and the stream is indexed by the number of iterations we have already done. So if we step once inside the stream, what we get in return is a value of type an and a new stream, which, when called, will produce a new value of type an plus 1. And as far as syntax is concerned, stacks are exactly constructors with values pushed on top of another stack, and computations are just things that pattern match on that stack to uncover one frame and capture the rest of the stack as a continuation. And so with that, we can recover the two sides of lambda armor with our call by push value semantics. We finally just had exponentials for sharing and fixed points for recursion. So in resource analysis, surprisingly, linearity we found is not as important as polarization, meaning that linearity is only required for resources, so for resource-bearing data. If resources do not hold potential, if data does not hold potential, it can and should be shareable freely, but only resources need to be unduplicated. On the other hand, polarization is very important because this is what defines the evaluation order of the program, and so which cost profile it's going to have. So we just had exponential. So this value ln alpha is in C is a shareable value which will produce a linear value, which will produce and return a linear value to a continuation alpha. And on the other side, once a value has been shared and duplicated, we just use a continuation ln on top of a stack S to produce linear value and feed it to continuation S. And we use the same, and we also fill out fixed points for recursion. So fixed points in the calculus are just terms that satisfy the fixed point equation. In an abstract machine, this just means that a fixed point is a value which is equal to itself applied to a certain continuation. So we just use that on the nose and say that a fixed point is a value in which self is applied to a continuation and then fed to some external consumer of that fixed point. So with this setup, we can manipulate our parameters, share values with those parameters, and consider iteration, and we have some consistency on which on the approximation we make of parameters at compile time. So typing judgments in our machine look like, so they have a parameter context, in which context have a type. They have a value context, in which the type of values is dependent on the value of parameters. We have a continuation context, which is also parameterized, and a command as a parameter context, a first order constraint on those parameters, and then variables and a continuation. And this means that for every assignment of parameters in thetas that satisfy constraint C, and variables that are typed in accordance with that, the command is well typed. This command is well typed, and this is preserved in some sense by small step semantics, in that if a well typed command reduces to another well typed command, then we have this implication for every parameter. And this is due to the fact that the machine corresponds to intuitionistic linear logic, and manipulation of parameters corresponds to the same manipulation done in sequent calculus and its proof of cut elimination, which we can reuse quite directly in our system. So now that we have this machine that can encode some kind of mix and match operational semantics and parameters, which can be approximated consistently, we can encode programming languages. So to do that, we just had some syntactic sugar to the machine, just saying that funcs are functions which funcs are functions that takes no arguments, so of type 1 lollipop t, and they return some data t. And so the syntactic sugar is just some command with a continuation, and this command, when run, will provide its computed value to alpha. And so if we have some func on one side of the machine, on the other side we can either force the func and get the return value, or we can just bind it to a name x and manipulate it without running it. Likewise, closures are data holding computation, and if some context wants to open the continuation, wants to open the closure can just let itself be opened, or it can force the context to be dragged into its scope of definition so that the computation inside of it remains well formed. And with those two syntactic sugars, we can define, for example, call-by-value semantics for our machine, in which functions from A to B become closure that take some data argument A and define a func that, when run, will produce some data of type B. So expression in the language become funcs that return some data, and using what we saw to manipulate funcs, we can implement the operational semantics of call-by-value languages inside the machine. Not only that, but we also have an effect system for it for free. So if we look at this type here, if we just redefine closures and funcs, so redefining closure to take an extra argument of type S, and func to return an extra argument of type S, functions become state-passing functions that get a state as input and a state as output, which we're going to use to encode resource manipulation. We're just going to pass resources this way in this universal effect system that we get for free with the machine. So that's Autobail and the effect system for amortized analysis. So what we do is we just define a data type, a state token with two parameters, P and Q, P being the free resources that the program has access to, and Q being the currently allocated resources. So, and we can define resource manipulation primitives just as constructors on that data type. So as the program begins, some constant amount of resources are free, and none of them are currently used. Then, when we allocate some value, we just move some resources from the free side to the allocated size, and we do the reverse when freeing those resources. And we also have some relaxation operation which can allow us to add imprecision to our static analysis to make the problem easier to solve. And what this implementation gives us is that the total amount of resources used in the machine, available to the machine, stays constant as reduction evolves by definition. So we have allocation and freeing primitives which keep the total amount of resources constant, which greatly simplifies proofs of consistency for analysis, which usually have to do quite some work to prove that as data is manipulated, potential stays constant. And the problem of finding a potential function just become, given some some lambda calculi with alloc and free put in, try to minimize this P0 parameter, which is used in the definition of the token. Finally, we can recover what lambda mode does with values in potential by saying that a shareable value that holds some potential phi of n is merely something that, when given a token with phi of n used resources, will freeze those resources, so make those resources available, and then we get a value without potential. And this notation lets us recover values with potential while staying correct regarding our state token. So the full analysis finally looks like this. So given a function from A to B, we translate it to callback push value with a continuation passing style, which makes evaluation strategy and computation context both explicit. Then, using some linear typing, we can recover data flow through the program. Then we add our state token using the effect system, and finally we type with parameters to get something that says a function works for every parameters n that satisfies some constraint C, and then will return some new state defined by some other parameters that satisfy another constraint. And the user of the function can choose which parameters go there, and the functions will return as well some parameters. So once we have a program gone through this entire pipeline and we have these types, the question that remains is, can we go from this type with parameters and first order constraints to an explicit formula for complexity? This is to say, can we get some polynomial that represents this complexity? So For some, analysis we can, for example, for polynomial complexity in ARA, we have that every single implication we have in the first order constraint we have set up so that it looks like X equals some expression implies C, which we can reduce by substitution. At the end of the day, those first order constraints used by ARA look like a combination of polynomials, applications of polynomials, and using the two quantifiers, but only conjunction and equality. And we can solve that using some heuristic which was previously implemented for ARA, which is we scholemize every variable bound by an existential quantifier. So we take our X, existentially quantified in some scope in which some variable Y's are in scope. We build a new multivariate polynomial and substitute X for P of Y. And once we do that for every quantifier, what we have is a system of equations, so a conjunction of equations on polynomial, and once we translate that to a system on their coefficients, we get some kind of nonlinear programming problems involving the coefficients A, K that we generated, and what we optimize on is a chosen AK, which is the leading term of the complexity of the whole of the program. So what we had at the end of the day is a new intermediate representation for type-based static analysis that can recover both call by name and call by value evaluation, and can be used to mix and match things with to mix and match evaluation strategies, enabling uses of monads and iterators in analyzable functional languages. This uses effect systems that we have built for it, and the good thing that we found is that we can factorize analysis by first solving all the semantic problem, going from the language to the machine, generating a first order constraint, and then separately this constraint can be solved, which means that if we want to add a new programming language to the analysis, we just have to redo the front end of the analysis, and if we want to add new complexity classes, we just have to upgrade the constraint solver separately, which was absolutely not the case for previous implementations of ARA as far as we can tell. There are still, of course, some open problems in that regard, which is one, we need good solvers for the kind of constraint generated by resource analysis. And also, if you want to represent fine memory management, we need some kind of region system or heap semantics for our programming language. Thank you very much.
So we have time for questions. Are there any questions? So, John.
Yeah, it's really rather than a question, it's a request for clarification in some ways, because you take your source language and then you translate it into something else, which may well preserve the meaning of the program, but where did you argue that it preserves the complexity? I mean, you rejected the operational semantics, which would be the obvious way to get something that you could analyze which corresponds, you expect, to the execution of the machine. But what you derive is something quite different from the original. And then you proceed to analyze that.
Yeah. So that's a very good question, and it's going to be a problem, I believe, in every resource analysis system that attempts to work with many programming languages. So the way that we prove that consistency is preserved is by using an intermediate representation in which we have the machine and cost semantics without without our effect system. So we go from the source language, let's say a call by value lambda calculus, with cost primitives, and we go to the call by push value machines with cost primitive, and we show that this translation preserves complexity in that case. And then we have a second translation which elaborates our state token through the program, and we show that this is consistent regarding the second semantics on the machine. So this factorization is where it gets used. It is what helps us prove consistency for high-level source languages, saying that if you have a call by push value semantic, if you can prove that the translation to call by push value with resource primitive is correct, then we can go the rest of the way.
Okay.
Yeah, thanks for the talk. So one nice thing about ARA is that it can also be extended for not only amortized analysis, but also expected amortized analysis.
Expected in which sense?
For example, my algorithm might make random choices, and then I kind of have the average over that. So is this also applicable for your approach, or would this be a problem?
I do believe there is one problem when it comes to consistency is, so if we look at our consistency theorem, which is here, what we get is that, here this constraints gives also some kind of model for theta, so a set of assignment of theta which is valid for this constraint. And this applications tells us that models are included in each other. So the reason this works for resource analysis is that we're doing upper bounds, and that the values of P and Qs that make the program correct can only be extended as the program goes on. So that is to say, if we evaluate the program past its peak resource consumption, or past some hard to predict step of reduction, the bound will get, so the bound, okay, let me explain again. Approximation becomes more precise as you run the program. At the end of the day, if you run the program if you run the analysis on a completed program, you know exactly what resources are manipulated, but at the beginning you don't know at all. So you have a refined approximation. And in our proof, we use extensively the fact that as the approximation gets better and better, the bound that we get can get lower and lower, because we're doing upper bound, and lower bounds basically means that models of bad approximation are included in models of good approximation. But I'm not sure if it works for average complexity. It's we're getting up. Yeah, but we're just doing upper bound, worst case scenario, basically.
Okay, I have one final question, because you can cover lazy as well as call by value semantics. Do you have examples where you have different amortized costs for the same program?
With lazy and
non-lazy and call by value?
Yes, so for example, if you take a list and you do a map then filter on it, if you use call by value, you will generate the intermediate list, which you don't want. And if you use call by name, you won't do that, because actually your lazy list will be some kind of iterator. And we can absolutely capture that in the system, and that's kind of the reason we want to have call by push value semantics, is we want to, in order to not have recursion all the time, we want to use iterators instead, which I believe are more tractable in general. So yeah.
Okay, thank you. Okay, so we run out of time, so thanks again for the discussion.